Good afternoon, everybody. My name is Michele Chiumenti. I'm working at CIMNE, which is the International Center for Numerical Method in Engineering here in Barcelona. I am professor at the Technical University of Catalonia. The work of today follow our development in additive manufacturing, and particularly in direct energy deposition process. And today, well, because of the timing that I have, I will focus on the thermal problem, the technology that we are using to deal with the numerical simulation of additive manufacturing. And I will go a little bit deeper into some small work that we did into the micro mesostructure simulation. So first of all, I would like to thank the work, the help of many people here at CIMNE involved in this kind of development, starting from the COMET group in which I belong to. But we are also, I have to thank the famous group, which is the new platform that we are using for the parallel computing that I will introduce to you in a moment. The discrete element group from Ognate and Sarate, that is not part of my discussion today, and the Git group, which is the pre and post processor that we are customizing for our needs. I also would like to thank the help of the postdoc and the PhD student, because their work really helped and push our development. So first of all, a small outline of the presentation. We are talking about additive manufacturing, but as you know, there are different kinds of technology. So I will go rapidly through to the different technology, and I will tell you which are the differences and which are the motivation of our work. So first of all, this is a slide which is quite classical, but I think it's very important to understand that there exist different time and length scales in additive manufacturing, and our work is fully defined in the larger scale. So we are using finite element with the scope, and the scope of our work is the thermomechanical analysis of the industrial process itself. So we are working at component scale, but it's also possible to work at the mel pool scale. It's also possible to work looking on the movement of the powder and this powder distribution, melting of this powder. And particularly, we had a nice work where we transformed the powder and defined as a discrete element into finite element once the melting happens. And there are also another scale, a lower scale, which can be tackled by phase field or cellular automata. There are different strategies, and all these scales work at very different time scales and length scale, as you can see here in my slide. As I told you, we are mostly focused on the larger scale, and so I will tell you which is our technology to tackle this component scale level. Even if we are talking about component scale, there are also large differences on the technology used in additive manufacturing. And so, depending on the technology, the layer thickness and the scanning speed are radically different. Radically different means that in wire feeding, we are talking about 800 to 4 millimeter thickness of the layer. So very large thickness of this layer, down to the powder bed technology, where the thickness is about 20, 30 microns. So 2 orders of magnitude smaller. But this is not the only problem, because also the scanning speed is radically different. So in wires feeding, we are talking about few millimeters per second, while in powder bed technology, the scanning speed is once again 2 or 3 orders faster. So the technology to be used for numerical simulation is affected by this. And actually, currently, it is still possible, or we can phase the numerical simulation of wire feeding and blown powder processes by a high fidelity simulation, while this is still different, this is still very difficult in case of powder bed technology. So in wire feeding or in DoD technology, our main goal is to perform a fully coupled thermomechanical analysis, and we look for the simulation of the exact process as it is going on in the machine. So we are following the heat source with its movement, and in fact we are reading exactly the same path as the machine does. So we are using and we are reading the G-code format of the machine, and we are reproducing this into our simulation tool. So we are looking for a very accurate solution of both temperature and stress field. Today I will show you a bit the framework that we are using and the temperature part, but well, in next occasion I will tell you something about also the mechanical part. Regarding powder bed, this is still, let's say, very difficult, and so typically commercial software, and as far as I know, this is really difficult to tackle. And so typically there are approximate solutions, typically based on inherent strain method in a layer by layer manner, or even multi-layer strategy. So it's completely different technology and completely different objective of the simulation. So why high fidelity analysis? Well, we are looking for high fidelity because we want to reproduce exactly what is going on at the industrial level, and this is because we want to get results which can be useful for the prediction of what's going on the part built by this kind of technology. So particularly, for instance, as input for the microstructure modeling, or to get relievable stresses, residual stresses from the simulation. In our opinion, this is possible only if the high fidelity simulation of the process is performed. Just as an example, you can see in the picture here at the left-hand side how accurate can be a simulation of additive manufacturing, including all the complexity of this kind of technology. So temperature dependencies, complex paths, complex boundary conditions, so on, but it's possible to obtain very accurate results. So we can reproduce exactly what's going on the thermocouple. On the right-hand side, you can see what happened if you just decrease the accuracy and you move arch by arch, or eventually layer by layer. So you can see that you, obviously, because of the conservation equation, you are preserving the average value of the temperature field, but you lose all the peaks. And so this is not what it can be useful for as a result, for instance, for microstructure modeling. So how to achieve this accuracy? Well, first of all, we decide in the last couple of years to move to an input which come directly from the slicer tool. So in this case, one of the most known slicer is Cura. And Cura is reading an STL of a geometry, and is doing the layering, the slicing, and generating the G-code. The G-code is the sequence of trajectory used by the laser to melt the material and to deposit this kind of material. So Cura is one of the possibilities. There are other kind of slicer, obviously, but what is interesting is that you have the possibility to get an output file in terms of a G-code, which include not only the trajectory, but is typically include the feeding rate, the cooling times when you are waiting for the cooling, the power source, the scanning speed, apart from the hatching. So in the same file, you can find all the information which are used to feed the machine. And we are using exactly the same information for the for the simulation. So in the interface that we have for the software that we are developing, the only thing that you really need is the definition of the material database. Typically, it's a temperature dependent material database, as you can see here. And the second information that you need is the definition of the layer thickness, which is typically also read from the G-code file, which is the difference of layering in the files. And more important, and in fact, one of the unique parameter available for the user, the number of uniform refinement level and Octree refinement level. This is used for the automatic generation of the mesh. So how it works? It works like this. In fact, we do not generate any mesh from the beginning. So the mesh does not exist. It only exists a bounding box. This is the only input which is automatically generated once the G code is read. So you have the bounding box where the part is defined. And then through a number of uniform refinement like this, so a Cartesian division of this bounding box, and next an Octree-based refinement like this, is possible to recover the geometry of the part. So this is done step by step, meaning while reading the G code, the mesh is generated. So the numerical process just move forward as in the actual machine. So the mesh is generated according to the hatch that is reading at the moment. So just to have an idea, if you are reading a first hatch, you will define a bounding box, a local bounding box of this hatch, where the mesh should be generated and activated. So here you can see that the mesh is generated within this bounding box, and the process just advances step by step. And in the lower picture, you can see 3 moments of this activation, where you can see how the bounding box advances and the mesh is generated. And you can see how this mesh is generated through an Octree-based refinement. So what the most important tool here is the adaptive mesh refinement tool, able to reduce the size of the mesh up to the size of the local bounding box, which defines the hatch. So this is what you can obtain. Here you can see how the mesh is generated following the path of the laser. How the Octree-based automatic mesh refinement works, and how the simulation go on. So for this kind of simulation, which is in fact a part from ArcelorMittal, we are using 4 mesh refinement, uniform mesh refinement, and 4 Octree refinement levels. So totally 8 levels of refinement from the unique cell which define the full bounding box of the component. Well, to work with this kind of accuracy, you need a powerful framework. And in this case, we are using FEMUS, which comes from the previous development of the group, of the FEMUS group, led by Professor Ramon Codina and Joan Bages here at CIMNE. This is an in-house finite element framework, which uses subgrid scale for the stabilization technology. It is an object-oriented Fortran tool, which used for the parallelization OpenMPI in both shared and distributed memory. Typically, we use it in distributed memory in large cluster. We are using parameters. We have different class of solvers. And we are using GitLab for the integration. Okay, so at the end of the day, we have a very powerful parallel adaptive framework, which can be used for this kind of really complex analysis. So the thermal analysis is based on the balance of energy equation. In strong format, this is what you want to solve. typically we skip in this case the mechanical dissipation, which is very small compared to the source. And we also typically neglect the latent heat if we are working at component level, obviously not if you are working at a melt pool. This is because typically, once again, the time scale at the macro scale is much larger than the one at the meso scale, meaning at the melt pool. So the heat necessary to melt the material is immediately released through the solidification. So again, typically we have all data which are temperature dependent, and what we need as input is the power source. This is given in terms of a gold double ellipsoidal power supply, but take into account that when you are working at the single track analysis, you typically make this source moving in a very slow motion, but at global level, meaning at component scale, the time step are much larger, so you typically use an average distributed power distribution. Next, and very important, is the heat loss. So the heat losses come mainly by radiation, so you typically use the radiation law, through conduction at the base plate. So this is explained why typically the grains are aligned in the vertical direction, because the flux is going on in the upper and the lower surface, while convection is used, is implemented through a classical Newton law, but typically this heat convection coefficient is much lower than the conductivity coefficient or the value of the radiation. I just want to rapidly go through what we did to try to catch some information from the thermal analysis. So we have two models implemented at the moment. One go through the microstructural evolution via JMAK models. So what we have here are two different kinds of implementation, one for diffusion transformation, typically from beta to alpha transformation, and the instantaneous transformation for the martensite. And this is in cooling, but because of the repeated cooling and heating cycle, you have also to take into account the heating transformation. So you have a diffusion transformation from the martensite to the alpha plus beta, and the instantaneous transformation alpha beta to beta. So typically, we need to integrate four kinds of transformation. The diffusional transformation are made via JMAK equation, typically very similar to the one used in casting analysis. The only difference is because of these two coefficients here, which take into account the previous transformation within the thermal cycles. Okay, the instantaneous transformation are used through empirical models. Here you can see once again the accuracy of the simulations in terms of the thermocouples, and this transforms into an accurate definition of the microstructure once the process being integrated. Finally, I just want to conclude with some result of one of our last paper. We have a blocks which has been simulated once again perfectly according to the scanning sequence of the machine. So you have this kind of hatching, repeated hatching following this kind of structure. Once again, the simulation is very nice in terms of thermal result compared to the experimental one. So they match exactly. We have 2 points of reference, one in the corner and one in the center. And what is interesting is that when we perform the simulation, you can see that the banding observed at the center and the band observed at the corner are quite different. Typically, in the center of the specimen, this banding is 2-layer thick, while at the corner it's 4-layer thick. And this is due to the different kind of heat accumulation at these two different zones. So typically here you have an heat affected zone which is 2-layer thick, and here it is typically 4-layer thick. So this is quite nice. And also we have used an integration of the time in which the temperature go in the alpha beta transformation. And if you integrate this timing, you can get an approximate definition of the grain size of the microstructure. So it is possible to integrate, to interpolate this value, and you can see that it's possible to define a law which is directly proportional to the integral of this gray zone here, where the material go through this transformation. A similar empirical law can be found for the hardness. So this means, once again, if you have a good numerical tool able to accurately define and follow the actual process as in the machine, you can exactly reproduce what's going on in the part. You can obtain a very good solution, at least in this case, I'm showing you the thermal solution, and this can be used as a good input for the microstructure, mesostructure analysis. So I would like to thank you for your attention. I apologize because I cannot show you all the results that we have. And I would also to thanks the help of the industrial and research partner for this kind of work. If you want to have more detail, you are allowed to ask me any question, and you can also refer to a number of references that has been published in the last year. So thank you very much, and once again, thank you to the organizer for this kind invitation and the possibility to show our work in the context of this very nice conference. So thank you very much.
Thank you, Michele. Thank you very much for your broad presentation. So I would open the presentation for discussion and questions. I don't see for the moment any question coming. So let me start with a couple of questions. One is very simple. The other one probably is, is not difficult, but strange. So you talked about average power energy distribution depending on the time step that you're using. So how do you apply this energy, like a uniform value over delta X, or how do you do it? So as a uniform.
The broad, the less accurate version, and well, in fact, in my personal opinion, this is not that important. Meaning,
yeah, exactly.
It's very important at the single track analysis, obviously, and this is extremely important to take into account how this power is distributed. While working at using this larger time stepping, this kind of distribution is not affecting the global result. Nevertheless, typically, each one of the section of this element are the same, but through the thickness go through an exponential law, like the Goldap one. So at the end of the day, it's a sort of very elongated ellipsoid.
Okay, I see. Okay.
But in any case, we did many simulation, and in fact, this does not affect really much the global result at the temperature level.
Okay, let me go to the other question very quickly, because now there are questions coming. You talked about high fidelity model for dead technology. So are you studying, are you modeling the powder distribution using a fluid mechanics model, or what?
This is part of the, let's say, mechanical part, the mechanical modeling. The answer is that we have two different constructive models, one for the solid phase and one for the fluid-like phase. In the fluid-like phase, in both cases, we are using a mixed formulation. In the solid phase, we are using a UP formulation. So this is a mixed displacement pressure formulation, which includes the stabilization and whatever for this kind of problem. While in the fluid phase, what we have is a VP formulation. So it's a velocity pressure formulation, which integrate a Norton-like rigid viscoplastic equation. So this is a fluid-like equation, which give you very good result in terms of pressure distribution within the melt pool and fluid-like behavior.
Okay, let me go now to question. Ernest Rank was raises hand. So Ernest, please.
Michele, thank you very much for this very nice presentation. A question, well, you mentioned, and I think this is really very important, that coarsening is as important as refinement, because otherwise you are running out of any possibility to really keep the degrees of freedom to a limit. So how do you do your coarsening of the potential, the temperature field? Is it by some projection? And the second part of this question, if one goes to the mechanics where you really have history variables, what are your experiences about coarsening there?
Well, obviously coarsening is extremely important, because without coarsening, as you said, it's impossible to maintain a reasonable number of degrees of freedom during the full process. We have just a projection method to extrapolate the value to the coarsened mesh, but this is enough for the thermal problem, but is not enough for the mechanical analysis. So if you have a look, I don't have the time to enter into detail, but if you have a look to this first publication here in this list, we define a method to retain the information of the fine mesh into the coarsened mesh. So this is a correction after the extrapolation of the value to the coarsened mesh to retain the same configuration as you had using the finer mesh. So this is an extremely important step that we didn't saw in other applications, and we could check that this is extremely important. So in this paper, you can find the detail, and effectively, this is really important if you want to switch to a coarsened approximation of your geometry.
Okay, thank you very much. Let's move to Paul. Paul also has a question. Please, Paul.
Yeah, maybe since time is running, just quickly. In our experience, I mean, it's the efficiency of your computational approach that is key, right? So, I mean, you have to be fast with your computations. Can you comment a little bit on the computational costs of your implementation, let's say on the single track level and on the component level? This example that you've shown, this build up of the entire component, I mean, what is the typical computation cost?
This is really depending on the number. The framework is fully is parallel and is fully scalable, very much scalable. So it really depends on the number of processors that you are available. Typically, we are running in a cluster with 50 processors, and all the thermal simulation that you saw run in few hours. If you move to mechanical analysis, you can multiply by 3. Typically. We are now working on reduced order modeling to speed up the mechanical simulation to get result in the same timing as the thermal analysis. But as I told you, if you have a good machine, and right now this is not that expensive, meaning we are renting the facility outside, it's an outsourcing, but the simulation scaled really well. So if you can run in 100 processor, you can really scale down the timing as much as is required. Mm-hmm. And as said before, the coarsening is essential. One important thing that I never said, but I think right now it's important, is that it is very dangerous to refine, coarsen, refine, and coarsen, because this typically destroys the solution. So if you want to run a mechanical simulation, and if you want to get accurate result, what we typically do is to have very much refined the last 3, 4, even 5 layers, where typically the historical variable are affected, say plasticity as an effect, and then the rest is coarsened. And this last layer are moved according to the build of the part. So effectively, you have a big coarsening in the lower layer, and you keep fine the last layer, and this move upward. So this make the simulation very good, and you only need the result of this paper, this correction, to preserve what you add in the fine mesh into the coarse mesh, but you did this only once.